For the longest time, engineering simulation has been all about a big trade-off. You could have accuracy, which is great, or you could have speed, which is also great, but you almost never got both at the same time. And that created this huge bottleneck in how things get designed. But today, we're going to talk about how artificial intelligence is just shattering that bottleneck, turning a slow, really painstaking process into something that feels, well, almost instant. So what does this revolution actually look like in the real world? Well, picture this. You've got a car designer and an aerodynamics expert sitting in the same room. They can tweak a 3D model, change a curve here, adjust a spoiler there, and they see the impact on airflow in real time. Not hours later, not days later, but right then and there. And look, this isn't some far-off sci-fi dream. This is the very goal that's driving this entire shift in technology. It's about letting people collaborate at the speed of human thought.
Okay, but to really get why this is such a game changer, we first have to appreciate the problem it's solving. That idea of real-time collaboration has been pretty much impossible for one simple reason. The price of getting it right, the price of precision, has always been time. And I mean a lot of time.
So the gold standard for accuracy in engineering, the way you know for sure that something is going to work, is what's called high-fidelity simulation. You've probably heard of computational fluid dynamics, or CFD. These methods are so incredibly accurate because they simulate the literal physics of air flowing over a car by breaking the problem down into millions and millions of tiny calculations. We're talking sometimes over 100 million of them. They are, for all intents and purposes, the ground truth.
And this slide right here, it lays out that core trade-off perfectly. On the left, you've got your traditional simulation. Yeah, it's incredibly accurate, but it takes hours, sometimes even days, for just one single run. So you only use it at the very end for validation. But on the right, you have AI prediction. We're talking results in milliseconds. This isn't for that final stamp of approval. It's for playing around, for exploring ideas right at the beginning of the design process, which is something you just couldn't do before.
So, how in the world did AI get smart enough to do this? Well, the models that can pull this off didn't just pop up out of nowhere. They're actually the result of this really fascinating evolution in how we teach machines to understand really complex problems.
The early AI for this stuff, called reduced order models, was kind of like a one-trick pony. It could get really good at analyzing one specific car design, but if you changed the shape in a major way, you basically had to train a whole new model from scratch. The real breakthrough came with deep learning. These new approaches like graph neural networks and transformers can actually generalize. They're not just memorizing the shape of one car, they're learning the underlying physics. This new flexibility all comes from a fundamentally different way of thinking about the problem. Instead of just memorizing a bunch of numbers, these advanced AIs are learning to actually conceptualize the physics in terms of shapes and fields. It's pretty cool.
So how does it actually learn? Well, one of the key methods is the graph neural network, a GNN. Think of it like this. Instead of seeing a car's surface as millions of disconnected dots, a GNN sees it as a web. It sees the points, the nodes, but crucially, it also sees the connections between them, the edges. This lets it understand how a change in one spot, say air pressure hitting the hood, is going to ripple across the surface and affect other parts, just like it does in the real world. And building on that is an even more powerful idea, the neural operator. So if a GNN learns the map of a car, a neural operator learns the rules of traffic on that map. It's not just memorizing routes between specific points. It's learning the fundamental physics, the operator, that explains how air will always behave when it hits a shape. And this is huge, because it means the AI isn't tied to the resolution of one specific 3D model.
And this leads to something that's, well, it's kind of mind-blowing when you think about it. A traditional simulation needs millions of data points to get the calculation right. But it turns out the AI doesn't need all of those points to learn the pattern. Researchers found that after a certain point, feeding the AI more and more data from the simulation doesn't actually make it any smarter. It's like the AI goes, okay, I get it now, I see the rule, and just giving it more examples doesn't add anything new. So this all leads to two really powerful approaches that are working today. On one hand, you have GNNs, which, as we just saw, are fantastic at understanding those local point-to-point relationships across the web of a 3D mesh. On the other hand, you have transformers, which actually borrow a trick from computer vision. They look at the problem in patches, which lets them understand the bigger picture, the global context, how large features of the car influence the airflow way on the other side.
Okay, so we've talked about the theory, but what does this actually look like when an engineer sits down at their computer? How do they really harness all this power and put it to work? Well, it's all about a new kind of partnership between traditional simulation and AI.
The whole industrial workflow really boils down to these three key steps. First up, preprocessing. You take hundreds of those massive gigabyte-sized CFD simulations and you intelligently condense them down into a format that machine learning can actually understand. Step 2 is training. You feed all these examples to the AI model and let it learn all the patterns. And finally, step 3 is inference. You give that trained model a brand new, never-before-seen geometry and it spits out a prediction in milliseconds.
Now, it is absolutely critical to understand this. AI is not here to replace those super accurate physics-based simulators, not at all. It's a partner, a complementary tool. And the quote on this slide just puts it perfectly. Think of it like a recommendation system. The AI learns from the gold standard simulations to give you incredibly fast, really smart guidance.
So what's the payoff? The practical benefits are just huge. You can suddenly explore dozens of different design ideas in an afternoon. You can instantly see which ones are duds and just throw them out. This frees up engineers to use those precious, time-consuming simulations on only the absolute best candidates. And it all comes together to enable that truly interactive design process we talked about at the very beginning.
And maybe the most exciting part of all this is that the AI doesn't actually know it's learning about airflow. It's just learning patterns and data. This means the entire approach is physics agnostic. You can apply the exact same method to totally different problems, like how heat moves through a computer chip, or the structural integrity of a bridge, or even electromagnetisms. As long as you have the simulation data to train it on, the AI can learn the pattern.
And that leaves us with this one last, really fascinating question to think about. This AI isn't just solving one specific problem. It's learning how to translate the language of geometry into the language of physics. So, if we now have a tool that can act like a universal translator for all these physical phenomena, what engineering challenges that seem impossible today will we be able to solve next?